Welcome back to the video series on integration and differential equations. In today's video, we're going to look at the situation where the auxiliary equation has complex roots. Let's start with a whirlwind refresher on complex numbers. So the symbol I represents the square root of -1. I stands for imaginary number. This is sometimes called J to avoid confusion with current. So you may see either I or J used as the notation, but I'm going to stick with I here. So what we want to practice is just how to simplify some complex numbers. Say we run into the square root of -7. We would simplify that by breaking that up into a product of square roots. So we'd say that's root 7 times root -1. And then the root -1 is just more simply expressed as I. So we'd call that root 7I. If we run into the square root of -4, we'll be able to simplify that even more. So using the same idea, we break that up into a product of roots, root 4 times root -1. And then the nice thing about this, root 4 simplifies to 2. And then our symbol for square root of -1 is just I. So 2I would be a simpler way of describing root -4. Okay, so we'll keep that in mind as we go through our examples. Here's our main idea for this topic. If the auxiliary equation has roots that look like alpha plus or minus beta I, then the general solution to the dE looks like this. Y will be an exponential function times an expression involving trig functions. And if we look at the exponential, it has the form e to the alpha x, whereas when we look at the sine and the cosine terms, those have angles that look like beta x. So you can see where those numbers alpha and beta come up in the solution. Alright, so I should point out that when we're solving auxiliary equations, if we do get a complex solution, these complex solutions always come in pairs. So you'll never just have one complex number as a solution. You'll always get a pair that looks like this. And that pair of complex solutions is going to produce a pair of solutions to the dE. So meaning these two different complex numbers here are going to produce two different solutions to our dE. So one of them is going to look like a cosine function times an exponential, and the other solution is going to look like a sine function times an exponential. All right, let's try some examples. Let's solve the following dE. I would point out that it is a homogeneous dE because we've got 0 on the right side here. And we do have constant coefficients. When we look at the coefficients of the y double prime, the y prime, and the y, in fact, all those coefficients are 1. So this is definitely an example of a homogeneous dE with constant coefficients. The reason why I stress that is because that is the condition that allows us to set up the auxiliary equation. So now we know it's valid to write down our auxiliary equation, m squared plus m plus 1 equals 0. Now we can solve this type of equation either by factoring or by using the quadratic formula. This particular equation is not going to factor nicely, so let's jump to our quadratic formula. M is going to be -b plus or minus the square root, b squared minus 4ac all over 2a. And specifically for our problem here, that's going to look like -1 plus or minus the square root of, under the square root, we're going to have 1 squared minus 4. So overall, minus 3 under that square root. And that's all over 2. So to simplify these roots here, I would take this root -3 and I would simplify that by saying, well, that's the same thing as root 3 times root -1, and then just express that root -1 as the symbol I. So m is equal to -1 plus or minus root 3i all over 2. And to make that even easier to work with, let's divide both of the terms in the numerator by 2. So m is -1/2 plus or minus root 3 over 2 times I. So we're in a situation where we found a pair of complex roots, and the roots are always expressed symbolically as alpha plus or minus beta I. So alpha represents the real part, which in our case is -1/2, and beta represents the coefficient of the I, so meaning the imaginary part, that'd be root 3 over 2. Okay, so now that we've got our alpha and our beta, we can plug in and write down our general solution, just following this formula here. So y would be e to the minus x over 2. So in the exponent here, we've got alpha times x. That's -1/2 times x. So I'm just writing that as minus x over 2 to be a little more concise. And then we're going to multiply that by c1 times cos of beta x. All right, so beta is root 3 over 2. That gets multiplied by x. And then we're going to go plus c2 times sine of that same angle, root 3 over 2 times x. So my caution here is just to make sure that you do have x's inside your angles. Those angles are supposed to be beta x, and make sure that you've also got an x in your exponent in the exponential. It is easy sometimes to forget those x's when you're rushing. So something you may have noticed here, we started with a real problem, meaning all our coefficients were real at the beginning of the problem, and what came out in the end was a real solution. So our solution here involves real numbers. If you put in a real number for x, you're going to get a real number for y out. But somehow, through the middle of the problem, we moved into the world of complex numbers. So complex numbers were used as a tool, as an intermediate tool for solving this problem. And if you take a more advanced course in linear algebra or differential equations, you'll be able to look more thoroughly at exactly where this solution comes from. For now, we're just going to focus on applying the solution. Let's try one more problem. We'll solve this dE by setting up the auxiliary equation. It's going to look like m cubed plus 25m equals 0. And let's pull out a common factor of m from these two terms, which would leave us with m squared plus 25. Okay, so we're going to set that equal to 0. So two different possibilities here. From the factor m, that gives us the possibility that m is equal to 0. And from the quadratic, we have the possibility that m squared plus 25 is equal to 0. So to solve this equation here, you could use the quadratic formula, but when there are only two terms on the left side, it's often a little bit easier just to take a shortcut. So we could say m squared is equal to -25, and then we can take square roots of both sides as long as we recognize that we're going to be getting both the positive and the negative square root. So m is equal to plus or minus root -25. Okay, now we can simplify this root. That's the same thing as root 25 times root -1. And so we can say m is equal to plus or minus 5i. So had you used the quadratic formula, you should have come up with the same solution there. Okay, so overall, we've got 3 different roots to this cubic equation. m equals 0 or m equals plus or minus 5i. So we use the symbols alpha and beta just to refer to the real and the imaginary parts of the complex number. So alpha is equal to 0 here, because you could write these roots as 0 plus or minus 5i. So when we write it that way, we can see explicitly that alpha is equal to 0. And let's identify beta as well. Beta is the coefficient of the I. So beta is 5. Alright, so in writing down our general solution, I suspect life might be a little bit easier if we work with the complex roots first. So let's try that. So with alpha value of 0, we would write e to the 0x times c1 cos of 5x, I'm using the beta value of 5 here, plus c2 sine of 5x. And since e to the 0 is just 1, we don't really need that first factor on there. So far we've got c1 cos 5x plus c2 sine 5x. And that takes care of the complex solutions. But remember, we've still got the root 0. So we need another term added on here. That term is going to have constant c3. And this 0 is a non-repeated root, so we're just going to use the form that we saw in our earlier video on distinct real roots. We're just going to use the form e to the mx there. And m, in this case, is 0. So again, that exponential there just becomes 1. So a cleaner version of that final answer then, our general solution, looks like c1 cos 5x plus c2 sine 5x plus c3. So that is one perfectly good answer. That's probably the easiest way to do it. The other way to do it, you could have handled the roots in the other order. So you could have gone with m equals 0 first, and you'd say c1 e to the 0x, and then you'd say, well, e to the 0 is just 1, so I don't really need that exponential on there. We just have c1. And then we'd move over to the complex roots there. Alpha is 0, beta is 5, so we'd write down e to the 0x times some other stuff, and again we'd say, well, e to the 0 is just 1, so we don't really need that part on there. We'll make the brackets a little bit bigger. Okay, and in fact we don't even really need the brackets, but I'll keep them on here just for clarity so we can follow along with what's going on. So we're going to need two more constants in here. Those constants will be called c2 and c3, and what we're multiplying them by, cos of beta x, beta is 5, so cos of 5x, and c3 gets multiplied by sine 5x. And then, as I mentioned, we could drop the brackets. They aren't really necessary there. So both of these are great as a final answer, and it really comes down to just which root you want to write down first. Two equivalent and good final answers. We've given our general solution to that DE that we started with. Thanks for watching, and we'll see you in the next video.